Today I'm going to be reviewing another paper that talks about fractals. This paper is called Turbulent Black Holes Grow Fractal Skins as They Feed. Okay, so this article, which was published in April 28th of 2014, is actually about this paper here called Holographic Turbulence. Okay, so again, we've got a lot of words in here that I find really fascinating. The word fractal, the word holographic, and the term black holes. Now I know, like the term electron, the term black holes seems to be a bit of a trigger term for some people that want to insist that black holes don't exist. Okay, so I don't have a problem with the term black holes. Black hole is a phenomenon like the electron. Black holes are a phenomenon. When I talk about black holes, I am talking about the phenomenon that is happening at the center of a galaxy. And it means more to me than that, but that is the starting point for the discussion about black holes. First of all, I find it really interesting that they are using the Mandelbrot fractal in this article, okay, because obviously I have my own ideas of what black holes are, as I describe in my paper, the Mandelbrot set as a quasi-black hole. And so when I ran across this back in 2014, I was really excited because I feel like, maybe mainstream is finally catching up with me and my ideas about the fractal nature of the universe. So the article reads as follows. Feeding black holes develop a fractal skin as they grow. That's the conclusion of simulations that take advantage of a correlation between fluid dynamics and gravity. We showed that when you throw stuff into a black hole, the surface of the black hole responds like a fluid. And in particular, it can become turbulent, says Alan Adams at the Massachusetts Institute of Technology. More precisely, the horizon itself becomes a fractal. Okay, and they're talking about the event horizon here. So the horizon itself becomes a fractal. And then they go on to describe fractals. Fractals are mathematical sets that show self-similar patterns. Zoom in on one part of a fractal drawing, like the famous Mandelbrot set, and the smaller portion will look nearly the same as the original. Not exactly the same. Self-similarity is not self-same. Now, I just want to point out, because this can cause a lot of confusion, there are a lot of fractals out there that are self-same, like the Koch curve, and there are other fractals that, when you zoom in, you find exactly the same structure at different scales. But in the Mandelbrot set, when you zoom in, you find similar. So the word similar is very important here, okay? One portion will look nearly the same or similar as the original image. Objects with fractal geometries show up all over nature, okay? They're saying it themselves. These experts are saying that fractals show up all over nature. Fractals are not just math. From clouds to the coast of England. Adams and his colleagues have now found evidence that fractal behavior occurs in an unexpected place on the surface of a feeding black hole. Okay, so this is where I'm not exactly convinced that mainstream knows exactly what black holes are. They say that black holes grow by devouring matter as it falls into them. The black hole at the center of our galaxy, this was back in 2014, is due to feast on a gas cloud later this year. Now, I'm going to talk about this a little later, but the details of how feeding black holes grow and how this might affect their host galaxies are still unknown. The important point here is that there are certain things about black holes that are still unknown by the experts. Okay, so I think it's important to realize that, science is not a belief system. Science is a method. Okay, science is you gather data, you do an experiment, you gather data, you interpret the data, and make some interpretations which you write in the conclusion section of a paper. And so not everything about black holes is known. There are still some unknowns. To investigate what the horizon of a black hole looks like at mealtime, Adams took advantage of a mathematical duality, a dual, between Einstein's equations of general relativity, which describe gravity near black holes, and fluid dynamics. Okay? It is my opinion that fluid dynamics is the key to understanding all of nature. It's the key to understanding, electronics. In fact, I showed you that video where Dan Winters says that electricity is fluid dynamics, and I happen to agree with that. And so fluid dynamics, the fact that they can map the math basically of Einstein's equations of relativity to fluid dynamics is a huge clue that fluid dynamics is in fact the dynamics of the universe. Physicists showed in 2007 that the equations describing fluids and black holes can be translated back and forth. They call that a dual. So there is a dual between black holes and the equations describing fluid dynamics. So playing these mathematical games, okay, they trivialize it to a game, but I think it's more than a game, can give insights into both systems. If a particular behavior is simpler in one regime, it can give physicists intuition about how things work in the other. So for sure, this is true. So trying to understand everything in terms of fluid dynamics, because fluid dynamics is something that we can have personal experience with. Okay, so fluid dynamics, there are a lot of knowns in fluid dynamics because we can study them directly. And so we can gain intuition about how things work in other domains, in other regimes, by studying fluid dynamics. Adams and his colleagues were curious about turbulence, a kind of churning fluid flow that shows up everywhere in fluid dynamics, from the way milk behaves in coffee to the way air moves beneath a plane's wing. So we have this duality, this dual between fluids and black holes, and we know the fluids do something fascinating. They go turbulent, says Adams. But we have no idea how this translates on the black hole. So the research led by Paul Chesler, who is a postdoc researcher at Harvard, the team first modeled a turbulent fluid system. They then translated it into the black hole regime and let it develop over time. When they looked again, the horizon of the black hole appeared to have developed an infinite surface area. An infinite surface area. That's the signal of having a fractal. Now, that's kind of a weird way of saying it. That's a signal of having a fractal. No, that is the signal of a fractal, says Adams. The area is infinite in the same way that the coastline of England appears to have an infinite length. And this was Mandelbrot's how long is the coastline of England discourse. Okay, the more you zoom in, the more detailed the shape becomes, and so the more space it seems to take up. The fact that it turns out you can just look at the horizon and it will be fractal if the fluid is turbulent, that is a surprise, says Adams. That was a delight. It was a surprise, a delightful surprise to Adams that this fluid turned out to be fractal. Okay, so this was not a surprise for me, though. When I read this article, I was not surprised that the surface, the interface between the black hole, inside of a black hole, inner world, and the outside of a black hole, outer world, was a fractal. This was not a surprise to me whatsoever. So just as an aside, I ran my own tests to see this increasing length of a coastline as you decrease the measuring stick of the fractal pattern. So what I did was I generated a series of fractal of Mandelbrot images, and I counted the number of pixels on the right at the border between inner world and outer world. And then I normalized the data, and in fact I do see an increasing coastline as I decrease the measuring stick. Okay, so what I did was I generated a series of images. This one was 200 by 200, then 400 by 400, then 600 by 600, and at each step I counted the number of pixels on the surface. And of course, since I'm making the image bigger, I'm going to be counting more pixels. So then I would divide by, so the second one I divided by 2 to get the values back to the, as if it was a 200 by 200 image. For the 2000 by 2000 image, I divided by 10, the number of counts by 10 to get back to the 200 by 200. And as you can see, these are the values, the normalized values that I end up with, and you can see that the length of this fractal boundary is in fact increasing as I decrease the measuring stick. Okay, so this, the coastline, it never goes infinite. They say infinite. It is maybe theoretically infinite. If I could have an infinitely small measuring stick, I could measure an infinitely long coastline. But that is not, in reality, there's always going to be a smallest measuring stick, and so this boundary is always going to be finite. So other than the use of the word infinite in this conversation, I agree with what they're saying here. So regarding this article, so turbulent black holes grow fractal skins as they feed, which is a really catchy title. But if I were writing the article on this, if I were going to write the title, I would title this "Black Hole Event Horizons Are Fractal." So that would be the title. If I were going to write an article on this, I would say the black hole event horizons are fractal, because that's what I see here. And I would use this figure. This is a figure from my paper, the Mandelbrot set as a quasi-black hole. Okay, so this is a figure from my paper, from this paper here, and where I am showing the morphological similarities between an actual galaxy and a region of the Mandelbrot set. And so if you look at these very closely, you will see a lot of similarities. Okay, so that is the Mandelbrot set as a quasi-black hole is my take on the idea that the event horizon of a black hole is fractal. Only basically what I am saying is that the galaxy itself is the fractal curve, is the fractal boundary of the black region in an actual galaxy, of a black hole in an actual galaxy. Okay, so that is just roughly what I'm saying, is that the galaxy itself is the fractal event horizon, is the event horizon of a cosmological black hole. So the event horizon isn't just in here. The whole galaxy is the event horizon of a black hole, according to my quasi-black hole theory. So I just want to quickly get back to this point that they were making. They say black holes grow by devouring matter that falls into them. I'm not entirely sure I agree with this. I don't think black holes devour anything. If anything, they recycle matter, convert it back to hydrogen, and then spit them out the jets. But anyways, so to test this, the black hole at the center of our galaxy was due in 2014 to feast on a gas cloud. They said later this year. Here are some of the headlines. A gas cloud colliding with the black hole at the center of our galaxy, and we get to watch it. Okay, so the gas cloud is going to, back in 2014, collide with the center of our galaxy, and we're going to get to watch it. The Milky Way snack time supermassive black hole to consume. This is a huge assumption, to consume a gas cloud. Okay, so let's see, there's another one. Milky Way's giant black hole to eat space cloud in 2013. So they knew about this back in 2011, actually. So let's just see one more. Gas cloud headed towards Milky Way's supermassive black hole. And then one more. Scientists hope to catch a glimpse of our sleeping black hole at the heart of our galaxy as it devours a nearby gas cloud. Okay, so this is what they expected to happen. The first ever observation of impact with a supermassive black hole. A rare glimpse of a black hole with a mass of 4 million times our sun. Collision will shred the gas cloud and provide black hole with new fuel. Okay, that's what they're assuming. Gas cloud being stretched out like spaghetti by enormous gravity. So they were seeing this, spaghettification. Okay, so what did they in fact see? What actually happened? Okay, so guess what? The gas cloud, which they were referring to as G2, survived the black hole. It didn't get swallowed up by the black hole. It survived. It did not do what they expected it to do. So in 2011, astronomers said they discovered a gas cloud, or a cloud of gas with several times Earth's mass, accelerating fast towards the supermassive black hole at the center of the Milky Way. The cloud appeared to be undergoing spaghettification, sometimes called the noodle effect. I love that, the noodle effect. Stretching and elongating as it neared, you can't see that very well, but as it neared the black hole. It was thought at first the cloud, which they called G2, would meet a fiery end as it passed into the Milky Way's black hole as early as 2013. Well, this was in 2011. They discovered it in 2013. They thought that it would collide, but it did not. Okay, it did not. But astronomers now say it passed closest to the black hole in the northern summer of 2014. So in 2014, they think that it got closest to the black hole, but it did not meet a fiery death, a fiery end. Okay, unexpectedly, our galaxy's black hole did not swallow it. So I'm suspicious of this whole black holes swallow material. At the very least, I think the material goes in and it gets recycled and shot out the jets. But that's just my opinion. And in the future we will maybe have a better idea of what's going on there. Okay, so instead G2 survived. It survived. Okay, and now they have their new ideas as to why it survived. Okay, but it did not meet a fiery end as they expected.
Where's the kaboom? There was supposed to be an earth-shattering kaboom.
So in terms of the principle of incommensurability, My black hole model, my quasi-black hole model, has the black hole occupying inner world, the photon sphere occupying outer world, and the interface between inner world and outer world is fractal, is a fractal, freakishly complex, one-dimensional, infinite, almost infinite, I don't like the word infinite, freakishly long, complex curve. Okay, Adams and his colleagues have now found evidence that fractal behavior occurs in an unexpected place on the surface of a black hole, whether it's feeding or not. Okay, so they assume that the fractal has to be there only when the black hole is feeding, and I'm saying that the fractal is always there and that the feeding just exposes it. So they say, more precisely, the horizon itself becomes fractal. So this is in the principle of incommensurability, there are two incommensurate principles, and at the interface between the two incommensurate principles, whether it be a phase transition or an ether discharge, or a fractal black hole, a quasi-black hole, the interface between inner world and outer world, counter space and space, whatever you want to call it, is often, if not always, fractal in nature. Okay, so this is sort of similar to what I was saying in the previous video about electrons. In the electrons on the brink paper, they're talking about a phase transition. When the electrons are behaving more spatial, the material behaves like a metal, and when the electrons are behaving more counterspatial, when they clump together, then the material behaves more like an insulator. And so, the principle of incommensurability as a teaching tool, even if this were a teaching tool, this is how I would teach all of these different subjects. I think, if at the very least it's a good teaching tool, but I think it is also a very good principle. It is a binary principle, that the universe is governed by binary principles that are incommensurate, that are, that don't have anything in common. But what they do have in common is the interface between the two incommensurate principles, which is phenomenon. So wherever there is phenomenon, basically something you can see, phenomenon, then you likely are experiencing the principle of incommensurability. Okay, so I'm going to leave it at that. Like I said before, this comes up over and over and over again. I've seen this many times in many situations. And of course, given that I've written a paper called The Mandelbrot Set as a Quasi-Black Hole, obviously I'm not talking about the relativistic black holes. I'm talking about the black holes the mathematical relativistic black holes. I'm talking about the black holes that nature makes, and I believe the black holes that nature makes are more like what I'm talking about and less like what the relativists are talking about. The relativists are basically, they're looking at one iteration maybe. That's one way of looking at it. So they're only looking at one iteration, generally, and the universe is continuously iterating itself in bringing itself into existence. And so, but that is another story. I hope you're all having a good day, and I will be back with more on the fractal nature of the universe and the principle of incommensurability.
It's infinite iterations of the Nautilus section of the Mandelbrot set. That's some good stuff. Look at all the infinite Mandelbrot sets. Here, brot, there, brot, everywhere, Mandelbrot.